Good morning, class. Today we're going to dive into a fundamental topic in mathematics, sequences. Specifically, we'll be focusing on two very important types. We will explore arithmetic and geometric sequences. By the end of today's lesson, you will be able to, first, differentiate between arithmetic and geometric sequences. Second, you'll be able to use specific formulas to find any term in these sequences. And third, you'll learn how to calculate the sum of a certain number of terms in a sequence. Finally, we'll cover some more advanced applications, including recursive formulas, the concept of an arithmetic or geometric mean, and even how to sum an infinite number of terms. Let's get started. Let's begin with our first type of sequence, an arithmetic sequence. An arithmetic sequence is a list of numbers where the difference between any two consecutive terms is constant. In other words, you are always adding the same number to get from one term to the next. This constant value is called the common difference, and we represent it with the letter D. Let's look at a simple example. Consider the sequence 3, 7, 11, 15, and so on. To find the common difference, we can subtract any term from the term that follows it. Notice the pattern here. 7 minus 3 is 4, 11 minus 7 is also 4, and 15 minus 11 is 4. The difference is always the same. So for this sequence, the common difference D is 4. The formula to find the common difference is therefore quite simple. It's D equals A sub n minus A sub n minus 1. This just means the difference is any term minus the term that came right before it. Now, what if I asked you to find the 100th term of that sequence? You wouldn't want to write out all 100 terms. We need a more direct way, a general formula. This is where the general and term formula comes in. Let's think about how each term is constructed. The first term is just itself, which we call a sub 1. A sub 1 is our starting point. The second term, a sub 2, is the first term plus one common difference. The third term, a sub 3, is the second term plus D, which is the same as the first term plus two common differences. And the fourth term is the first term plus three common differences. Do you see the pattern? The number of differences we add is always one less than the term number. This gives us our general formula. The nth term, a sub n, is equal to the first term, a sub 1, plus the quantity n minus 1 times the common difference, d. Let's use this formula to find the 20th term of our example sequence, 3, 11, 15. We need to find a sub 20. We know the first term, a sub 1, is 3, the common difference, d, is 4, and the term number n is 20. Now we just plug these values into our formula. A sub 20 equals 3 plus the quantity 20 minus 1 times 4. This simplifies to 3 plus 19 times 4. 19 times 4 is 76, so a sub 20 is 3 plus 76, which equals 79. So the 20th term in this sequence is 79. Much faster than writing them all out. Next, let's talk about adding up the terms in an arithmetic sequence. This is called finding a partial sum. We use the partial sums formula, and the sum of the first n terms is denoted by S sub n. There's a famous story about the mathematician Carl Friedrich Gauss, who, as a schoolboy, was asked to add all the numbers from 1 to 100. He did it in seconds by realizing that if you pair the first and last number, 1 plus 100, the second and second to last, 2 plus 99, and so on, you always get the same sum, 101. He just had to figure out how many pairs there were. This is the logic behind the formula. The formula for the partial sum is S sub n equals the average of the first and last terms, which is a sub 1 plus a sub n all divided by 2, and then multiplied by the number of terms, n. Let's find the sum of the first 20 terms of our sequence, 3, 7, 11. We want to find S sub 20. We know the first term, a sub 1, is 3. The number of terms, n, is 20. And from our last calculation, we know the 20th term, a sub 20, is 79. Now we substitute these values into the partial sum formula. S sub 20 equals the quantity 3 plus 79 divided by 2, all multiplied by 20. This becomes 82 divided by 2, which is 41, multiplied by 20. So the sum of the first 20 terms is 820. Again, this formula saves us a lot of tedious addition. Now let's move on to our second major type of sequence, the geometric sequence. While arithmetic sequences involve a common difference, geometric sequences involve a common ratio. This means you are always multiplying by the same non-zero number to get from one term to the next. This constant multiplier is called the common ratio, and we represent it with the letter r. Let's look at an example. Consider the sequence 2, 6, 18, 54, and so on. To find the common ratio, we can divide any term by the term that came before it. 6 divided by 2 is 3, 18 divided by 6 is also 3, and 54 divided by 18 is 3. The ratio is always the same. So for this sequence, the common ratio r is 3. The formula for the common ratio is therefore r equals a sub n divided by a sub n minus 1. This means the ratio is any term divided by its preceding term. Just like with arithmetic sequences, we need a general formula to find any term in a geometric sequence without listing them all. Let's look at the general nth term formula for geometric sequences. The logic is similar. We start with the first term, a sub 1. A sub 1 is our starting point. The second term, a sub 2, is the first term times 1 common ratio. The third term, a sub 3, is the second term times r, which is the same as the first term times r squared. The pattern here is that the power of the ratio is always 1 less than the term number. This leads to our general formula. The nth term, a sub n, is equal to the first term, a sub 1, multiplied by the common ratio r raised to the power of n minus 1. Let's use this to find the seventh term of our example sequence, 2, 6, 18, 54. We need to find a sub 7. We know the first term, a sub 1, is 2. The common ratio r is 3, and the term number n is 7. Let's plug these values into our formula. A sub 7 equals 2 times 3 raised to the power of 7 minus 1. This simplifies to 2 times 3 to the 6th power. 3 to the 6th is 729. So a sub 7 is 2 times 729, which equals 1458. The seventh term is 1458. Now, how do we sum the terms of a geometric sequence? We have a different formula for this. Let's look at the partial sums formula for a geometric sequence. The derivation is a bit of an algebraic trick, but the resulting formula is very powerful. The formula is S sub n equals a sub 1 times the quantity 1 minus r to the nth power, all divided by the quantity 1 minus r. It's very important that r does not equal 1, or we would be dividing by 0. Let's find the sum of the first 7 terms of our sequence. 2, 6, 18. We want to find S sub 7. We know a sub 1 is 2, r is 3, and n is 7. Let's substitute these into the formula. S sub 7 equals 2 times the quantity 1 minus 3 to the 7th power, all divided by 1 minus 3. 3 to the 7th is 2187. So we have times negative 2186 divided by negative 2. The 2's and the negative signs cancel out, leaving us with a sum of 2186. Let's briefly touch on a few other important formulas from our sheet. First, recursive formulas. Recursive formulas. A recursive formula defines a term based on the term before it. It's a different way of thinking about the sequence. For an arithmetic sequence, any term is the previous term plus the common difference. For a geometric sequence, any term is the previous term times the common ratio. These are the simplest recursive definitions. Next, let's discuss the mean or average. The mean or average, the arithmetic mean of two numbers, a and b, is the number you would put in the middle to create an arithmetic sequence. The formula is simply the standard average, m equals a plus b divided by 2. The geometric mean is the same idea, but for a geometric sequence. The geometric mean of two positive numbers a and b is the square root of their product. For example, the geometric mean of 2 and 18 is the square root of 36, which is 6. And notice 2, 6, 18 is a geometric sequence with a common ratio of 3. Finally, let's consider a fascinating question. Can we add up an infinite number of terms? This is the concept of an infinite sum. For an arithmetic sequence like 3, 7, 11, the terms just keep getting bigger. If you add them forever, the sum will go to infinity. So there's no finite sum. That's why our formula sheet says not applicable, or NA, for the infinite sum of an arithmetic sequence. But for a geometric sequence, it's a different story. Consider the sequence 4, 2, 1, 1/2, 1/4. Here, the common ratio is 1/2. The terms are getting smaller and smaller, approaching 0. In cases like this, where the terms shrink, the sum can actually approach a specific finite number. This is called a convergent series. The condition for this to happen is that the absolute value of the common ratio r must be less than 1. If this condition is met, we can use a simple formula for the infinite sum. The sum to infinity, s sub infinity, is equal to the first term, a sub 1, divided by the quantity 1 minus r. Let's calculate the infinite sum for our example, 4, 2, 1. The first term, a sub 1, is 4. The common ratio r is 1/2. The absolute value of 1/2 is less than 1, so it converges. Plugging into the formula, we get 4 divided by 1 minus 1/2. This is 4 divided by 1/2, which equals 8. So if you could add all the infinite terms of this sequence, you would get exactly 8. All right, let's quickly recap what we've learned today. We've seen that arithmetic sequences are built on addition using a common difference d, while geometric sequences are built on multiplication using a common ratio r. We established our first learning objective, to differentiate between these two types of sequences. We then learned the key formulas to find any specific term, the nth term, and to find the sum of the first n terms, the partial sum, for both types of sequences. This covers our second and third objectives. And finally, we explored recursive definitions, the concepts of arithmetic and geometric means, and the powerful idea of an infinite sum for geometric series where the ratio is between -1 and 1. This fulfills our final learning objective. This formula sheet is your toolkit for solving problems involving these sequences. Practice using it, and you'll become very comfortable with these concepts. That's all for today. Great work, everyone.